it's a bit too late there.
Jordan. Now you just trying to get Eddie.
Okay, here we go. So, moving on. So today we're talking about moving charges through electric fields and through magnetic fields. But we're gonna basically treat them separately. We'll actually mash them together for a brief amount of time next class. Okay. So we do have some equations that we talked about before, and we're going to talk about them more. We're going to expand on that knowledge here. But we are, just like we started to compare, when we started to talk about charges, we spent a lot of time comparing them to masses. And so how there's like the force on the mass and the force on the charges, and the things that are different and the things that aren't. And we also learned about the motion of the masses way back in the first chapter, back in August and stuff. And then we learned about the forces and how the forces control our motion as well. So we're gonna see the same thing here. Let's talk about the motion of the particles through the fields. Let me grab my book again. I've been, my mind is still stuck in astrophysics because that's what we're doing in our IB 2-3 class. So I've got to switch gears and it's taking a little bit of time. So, darn it, for the, here it is. Where the equation sheet is. Duh. Okay,
No.
particles. Oh yeah, okay, so let's go back. When we talked about how if we had two parallel conducting plates and we're attaching a battery to it, so the battery is going to have a positive side, the long side is the positive side, the short one is the negative. So we've already discussed how this side is going to be the positive and then this side is going to be the negative. And we're setting up a uniform electric field. So far, this is still a review. So where do the field lines go? Which direction will they flow here?
To the positive.
They're going to flow from the positive into the negative. So in this case, the E field points up in the region of space. We're going to assume that we are well within the boundaries, so not close to the edges because it gets a little wonky at the edges. So definitely in the inside. And we also learned that it doesn't matter where in it, how close we are to one plate versus the other or side to side. It's all going to be the same electric field strength given by the equation E equals V over D, where of course D is the distance between the plates, and then V of course is the voltage that we apply to the two plates to get the charges in there in the first place. Okay, and then we also have learned based on the field is going to exert a force acting on the charge that's in the field. So if I had, let's say, a positive charge right here. Where's the force acting on the positive charge? Remember, the force is going to be pointing in the same direction as the field for a positive charge. So it's going to point up. Yeah. So our force points up. If I were to let go of this proton, what would happen?
It would stay.
Still go up.
Would it go through the plate?
No.
No. In fact, if it were touching the plate, it wouldn't go anywhere because it's already there. Like there's no space to move. Okay. But if I were to drop it down here, if I were to start here and I let go, what would happen? It would go up. Would it go up at a constant speed?
No.
Probably not. It would accelerate, right? Yeah, because we know that the electric force is a lot stronger than the force of gravity. So we're going to assume that it is true, in this particular case, that the E field is strong enough that it's just going to accelerate up. So I'm going to erase that first part. There we go. So it's going to accelerate up. It's going to gain a certain amount of speed and a certain amount of kinetic energy as a result. We haven't really talked about electric potential energy in this class, not yet, okay, and actually not in this chapter. It's going to come later because it's an HL topic, and we'll talk about that later as well. But if we were to consider, okay, well, how much energy does it gain as this charge is accelerated through a potential difference of the voltage here? It's a fair question. Let's take a look. So the energy that it gains, which is really the kinetic energy final, because of course it starts to rest, okay? So is equal to, well, really it's our work done acting on the particle. Remember work? Yes. So remember work was force times the displacement times the cosine of the angle. In this case, the displacement, well, it's just going to go straight up. So since the force and the displacement are exactly aligned, the angle is 0, cosine of 0 is just 1, so it's just our basic force times displacement. Okay, well let's keep trucking. So let's get an expression here. So the force, well, I've got the force equation here. Force is going to be the Q times E as we solve for F. So Q times E. And then my displacement was that D in this equation. QED, which is actually a Latin abbreviation for something. I forgot what it was. That's okay. But it's not going to stay like that. In fact, I want to substitute because I really want to get an expression based on the voltage of this. So I'm going to plug in this V over D in for the E right there. All right? So let's do that. So Q V over D times D. Huh, that's interesting. The D's cancel. Interesting. And we get the work, which really is equal to the final kinetic energy, or the amount of energy that we have gained, is equal to Q times V, where typically we're going to be talking about like a proton or an electron. So the charge of one proton or one electron is going to be the elementary charge, which its symbol is E. So it's really the gain in kinetic energy is really equal to EV. Now, if I were to plug in what exactly the charge is, remember that the charge of one electron, which we could look it up in our equation sheet, 1.6 times 10 to the negative 19th coulombs, times, let's just say 1 volt. Okay, let's keep it nice and simple. Okay, well, there's not much math to do here, so that's going to give me 1.6 times 10 to the negative 19th joules. It's a really small amount of energy there. Okay, so it might be helpful, and we'll see this in the future as well, that whenever we're talking about particles and their energies, it is often useful to express this in terms of EVs. Like, just like this says here, if we accelerate an electron or a proton through a potential difference of 1 volt, we will get 1 EV worth of energy. Yeah, so that's just going to be a more useful unit in expressing small amounts of energies. Just like if you've heard, we might have actually mentioned it before, but whenever we're talking about like astronomical distances, like how far a planet is away from the sun, instead of saying, you know, however many 10 to the 15th meters, okay, which is a lot of meters, we would say something in astronomical units, or 1 AUs, or like 5 AUs, okay, because the unit is more appropriate for that particular scale. So we'll see that in the future as well, usually, mostly for next year, okay? But, so knowing that if a charge is accelerated through a potential difference. It's almost like when we went to Busch Gardens and we rode the cheetah hunt. Okay, there was this strip where it accelerated you through a particular distance. So it's kind of like that, where any charge is going to gain a certain amount of energy as it goes through the field. Okay? Now, I wonder, how fast would it be going if it were to accelerate from here to here, knowing that this is the amount of kinetic energy I have gained? Sounds like our next challenge question. Oh, look, yes it is. Hold on. Let me try to zoom in so you guys can see this better. There we go. All right, challenge question live on the screen. Yeah, I saw that.
We are anyway trying.
What's the section we're in?
Huh?
What's the section?
What's the section?
D.
Oh, D3.
That's what I thought.
Yep.
You know, like calorie from rest, spectral difference, what is the maximum speed?
That feels weird all of a sudden.
Man, going on a whim here.
Shake it out. Shake it out.
Oh.
Jordan, I got a review guide with your name on it.
Wait, we're already having a test?
Well, there's one more lesson. So, test on Friday. Next week.
Oh my God. Friday, test on Friday.
Leave me alone.
Why not?
Wait, our test is on Friday?
Wait, you're giving a test on Valentine's Day?
Did
The
you
day
love
of
to take
love?
tests?
No!
Oh.
You're breaking my heart, Mr. Maynard. Breaking my heart.
Can't find a meeting. The
I honestly miss one of those classes. It's so bad, bro. I remember I started having like a dream mid fucking class. I was falling, so I was like that. My whole computer shook, and I just looked up, and I'm looking around, I'm like, yo.
I did that one time and I like pushed my hair off and like, what? Why?
What did she put?
He spoke it. I was saw it. And I don't know what happened. I wasn't even tired. Bro,
You were so dead.
bro, I was so far.
It was after, like, she taught everything and she was like, okay, y'all do what you want to do.
No, it was learning.
I was gone.
It was from the start of class to the end of class.
She was like, Dana, get up and be productive. I was like, I'm dead. She was like, no, you're not. I was like, I am. So I took a piece of paper out and I was just holding my pen in my hand.
That's what I was okay.
Hey, how was that test in this class?
Yeah, it was.
Balance.
Any specific questions? Just testing it.
She gave me
It was very non-scientific.
You
It's
could,
the
every
wig.
single question you could find in your notes
It's the wig, bro.
with
Alright,
an
let's take a look
explanation
here.
on
What are your answers
exactly
here?
how to
So we
do
got
it.
some B's, but then we're changing to some
Very
A's.
elegant during
Alright, I'm gonna call it 3, 2,
The free response
One.
question
Done.
on the back of one
Here we go. Okay.
not very elegant.
So,
calculator.
an electron is accelerated from rest through a potential difference of V.
Just like slightly different.
Thanks. What is the maximum speed of the electron? So knowing that we've already done part of it for you, so the kinetic energy gain is equal to E times V because E is the charge of an electron. Okay? So knowing that the kinetic energy equals E times V, and we know that the kinetic energy is just really 1/2 mv squared is equal to EV, and we're gonna solve for V. Keep in mind though, that we've got two different V's. This is big V, that stands for voltage. That's small v, it stands for speed. They do not cancel out, because they're not the same thing. Okay, so resist the urge to swipe them away. So we're gonna multiply both sides by 2, and divide both sides by m, and take a nice square root. So square root of 2 EV over m, and that means
D.
A is the correct answer.
That's just a big
Yeah, 2 EV over m. Square root.
Oh, yeah,
Yeah.
yeah.
A is the correct answer.
Hey.
Hey, yeah, there you go. All right, here we go. Who was the first one to choose A? Looks like Team Tara taking first place. Good job. Followed by, let's see, Quantum is in the mix here. They've got second place.
Jordan.
And then we've got Up and
I need
Adams
to go on timeout.
there with that third place point. Excellent, excellent. Okay, good. So, moving on. So now we're gonna try to focus more in on, well, so this is the motion in an electric field. So, and we had an object starting and rest. But what if it wasn't starting and rest? What if it was, let's say, see, it's weird. If you were to record each class, like, it's never the same thing twice, because I'm always thinking of different things. And so you guys actually happen to get
The best version?
the benefit of me messing up for the first two classes. So there you go. Yeah. So, let's say though that we had we had an electron. Okay. First of all, which way is the force acting on this electron?
Down.
Down. So the force points down. So let's say that I had an electron that was going up initially. What would happen?
It decelerates, right?
Ooh, decelerate is not really a word that we would use in physics.
Go down.
Just
Accelerate.
It negatively accelerates.
Negative acceleration.
Accelerate's the opposite direction.
But see,
Clockwise,
remember,
counterclockwise.
the negative sign on velocity and acceleration just tells you direction. It doesn't tell you speeding up or slowing down. So let's just use the simple words of speeding up and slowing down.
Speeds up in the other direction.
Counter
It'll
accelerate.
slow.
So
What
if
do you
it's initially going up, but the force acting on it is down, what's going to happen?
It's gonna go down.
Speed.
It's gonna stay. It's gonna stay.
Initially, it's
gonna
just going to drop down,
gonna
even though it's
stay-
going up initially?
It's gonna go
Just
up and
slow
then it's gonna
down.
slowly start to counteract itself and start to go the other direction.
It's gonna stop.
So it's going to go up, but as it goes up, what's happening?
Slows down.
It's slowing down. There we go. And then eventually it's going to
Stop.
stop.
And
And then, but is it going to stay there? No. No, it's going to start to accelerate downward. Kind of like
This is really dumb.
an object in free fall. Yeah. So it's going to go up, and then it's going to come back down. Good. Now, if we had a proton over here, where's the force acting on the proton?
Upwards.
Up. So if the proton were going down initially, what would happen to the proton?
It'll go down, slow down.
It would go down. As it goes down, it slows down. It reaches a maximum or minimum height, whatever. It goes down and stops at a particular point, and then it starts to accelerate upward. Good, good. All right. Well, that's 1D motion. What about 2D? What if we had, let's go back to the electron here, and the electron is going, just kidding, proton. Proton is going this way.
Okay.
Why are you that
Where's
way?
the force acting on it?
Upwards.
Points up.
Yeah,
So where will it go?
right here.
Kind of like
It'll curve
Diagonal.
in a parabolic path.
Mr. Manny, you do not make this easy to take notes on. I've driven,
Yeah.
I've rewritten, like,
Drawn.
I'm on my fourth one right now.
Why don't you do it in different colors, Jordan?
Because I don't have colors.
I have
Dana.
colors.
I'm sorry. Continue.
All right.
That's why I'm taking
Good.
those.
Now, but let's go back to the electron though. So the electron, where's that force pointing?
downwards.
Downwards. Okay. And if it were going to the right, I'm sorry, to the left. That's left, not right. Left at a speed v. What will its path look like?
It'll go down to the left parabolic.
It'll go kind of like that, like a typical mass in the presence of a gravitational field. Good. Good. Okay. So, motion in an electric field. Let's switch gears. Because we talked about the electric field, but now let's talk about magnetic fields. Is there something I need to do before that? No. Cool. Okay, so let's switch gears. The sound effects are free, there's no charge for that.
Oh wow. Better than Netflix.
No, it's not.
No, better than Disney Plus with the ads. It's killing
Disney
me.
Plus.
You have ads?
Bro, they're gonna be turning
You
this
have to
down in the
pay
future, bro.
for no ads.
To get audio for the movie,
For
you gotta
Disney
pay an
Plus-
extra $5.
Disney Plus, if you have a Hulu subscription, then it makes it like it plays the ads for the movies that are from Hulu.
No, it's disgusting.
So if I don't have Hulu subscription, then I won't have ads.
Well, no, you still
No.
have ads because Hulu's lame-ums and they make you watch ads.
I don't like this.
I've never watched the ad in my life.
Alright, let's get back to this. Yes.
I've never watched the ad in my life on Disney Plus or Hulu.
Because you don't
On
choose red
Hulu.
movies.
I've never watched that.
Spoiled butt.
I think we just pay for no ad.
Oh, just pay for no ads.
Oh, God.
Bro, it's $6 a
Oh,
month. Disney Plus.
It's not $6.
Disney Plus is
It's like-
$30 a month without ads.
It's like
Not
20.
bad.
Do you get the
No
bundle?
ads. It's like $24 a month.
$30.
That's insane.
Yes, me too. Yeah.
Can we talk about the physics of these ads and the
Let's
duration?
wrap up the
I'm
E
sorry.
field. So like, let's say wherever the E field was pointing, I'm not sure if it's pointing up or down, wherever, but it doesn't matter. So here's a new picture. Sorry, Jordan. But hey, it's new, so there you go. I'm not just changing the old one. So just to clarify, if we've got a positive charge and it's going this way, which way will it go?
Upwards, right?
It would sweep up.
Yeah,
Okay.
whatever. Yeah.
Okay. And if we have a negatively charged thing in an electric field, which way will it go?
Go down, sweeping down.
It'll
Right.
be deflected down. Then what if we have a neutron?
Wouldn't it just go
It
straight?
just passed through.
Unless like gravity.
A
So
neutron just chilling, right?
what kind of charge does a neutron have?
None.
No.
No charge.
So if there's no charge, then there's no force from the electric field.
So
And it's just going to keep on going straight.
I was right.
I want to be a
Like
neutron.
me.
I want to be a neutron.
You
Yeah.
I go
It doesn't make
go
any sense.
straight.
Yeah, go straight through the
Go
whole
up or
school
down,
year
straight.
and
I'm just
somehow pass.
I'm
It's
just straight.
amazing.
I don't see.
Yeah, sure.
Actually, a proton.
So say there's like a proton or
Being a
electron
proton is for
that is,
triverse.
like in an electrical field. Is there any way that the force of it can go through the electric field and keep going instead of like just following the path? Like, is there an amount of force that can force it out?
Well, I guess it really depends on how big the region is that the electric field is in. Because eventually the charged particle is going to reach some sort of barrier. And once it gets out of the field, then it no longer has that force acting, and then it will be going in the same direction along a straight line that it last was when it was in the field.
So if it was going in as in a diagonal direction and it got out, it wouldn't go in diagonal, it'd just go the way it was going, or would it keep going diagonal?
I think it would stay going.
So if it entered in a diagonal,
If it entered in like a straight line, but
Okay.
it curved diagonally, but it shot out, would it keep going diagonal, or would it go?
so if this were the boundary of where the field existed, and it's going in this particular way at that point, it's going to keep on going in that straight line. It's not going to keep on curving because the force causing it to curve is no longer there. Good question, good question. All right, let's talk magnetic fields now. Yes, magnetic fields. So, last time we learned the Bill equation, the force equals Bill, but there's actually another part to it, and the equation itself is found in this section, the D3 section, And there's a little sign of the angle action. So let me showcase for you where this thing is. So let me use, yeah, blue. So let's say that the V field in a region of space points up. Okay. And then our a wire that we talked about last class. So a current flows through the wire, and there's a force acting on it because the current itself creates its own field, and the fields interact with each other. We talked about that last class. But all of last class, we had our wires perpendicular to the field. So, but what if it's not? What if the wire and the current of the wire is flowing in this direction? The B field is pointing up. What's this angle that is in the equation? The angle is in between the current and the B field directions. So, and we've played with our sines and cosines enough that it should be kind of second nature, as in what gives you maximum and what gives you zero. So, when the wire is perpendicular to the B field, the angle is 90 degrees and the sine of 90 is 1. So we have our F equals Bill, okay, our maximum amount of force. But as we tilt that wire, the angle changes and the force decreases until we reach completely parallel to the field where the angle is 0, and therefore the force is 0. Very interesting. So it does matter the orientation of the wire in the field based on that angle. So we get the maximum amount of force on the wire here, but if the whole point is to have no force acting on the wire, then you would want your wires to run like this in the same direction as the magnetic field.
So it's like torque?
Torque will be involved. It's going to come back to next class.
Okay.
Torque with a spin.
Yes, because we'll
twist.
see how if we've got a loop of wire and it's allowed to rotate. Yes, that's coming next class. Yeah, sneak peek. Okay, good. Now, there is another equation in this section, and that talks about the force acting on a charge. Since we already know that a current passing through a wire is basically the flow of positive charges, the forces, the force acting on the wire is really acting on the charges in the wire. So if we look closer, let's say that we have just one just one charge, like a positive charge, and it's going at a certain v through the magnetic field. So this force acting on the charge is going to be equal to QVB times the sine of the angle. So the larger charge we have, the faster it's going, and the stronger our field strength, all will increase the force acting on that charge. But this is the very interesting part. So how much force there is really based on what direction the velocity is pointing in, which is completely different than over here. Over here, it didn't matter where it pointed, the force was constant for an electric field. The magnetic field, the force is going to change if the object is changing its velocity direction. So let's see. Okay, so again, we will get maximum amount of force if the velocity is perpendicular to the field. And we get zero force if we're in a parallel direction. Okay, so no force acting, even though it's a charged particle, there's no force acting on it if it's going exactly along the field or exactly against the field, as opposed to the electric field, which is different. Okay, so things are a lot more interesting with the magnetic force. All right, now, how do we find the direction of the force on a charge as it moves through the field? Well, we use our right hand rules again. Hope you brought your right hands to class today. Yes.
Oh, dang it, I
So-
left it at home.
Remember how we did it for the force acting on
That's
the
stupid.
wire? So we point with the current, we bend our fingers to point with B, and then our thumb points in a direction for the force. So I, B, force. Instead of I though, we have the velocity vector. So that's going to be where we're going to pointing, where we're pointing our hands initially. All right. So we're going to point up at an angle like that. Okay. Now I should be able to move my hands any way I need to in order for me. Y'all.
Be mature about this, y'all.
Just don't
I
connect
can't
it.
think about it.
Just don't connect it.
Yeah. Well, too late. Sorry.
It's a dark time for engineers, man.
I would have never
So-
known about this if you didn't do it, bro.
So I'm pointing my hand up like.
Right.
Because that's actually how I need to point my hand, because if I point my hand like this, and I bend my fingers down, that's not where my B field points.
Right.
No. Okay, I gotta have my palm up, because I gotta, after I point with V, I bend my fingers towards B, because they point up, and my thumb points where?
To the out.
Out of the
that
board.
works apparently.
Out of the
That
board.
works apparently.
What is that?
Okay, so out means point, right? So the force points up, out. Now,
Alright, let's just not.
He just ate.
where would this go? Like, what is the shape of the curve, if it curves at all? Like, what's happening here?
Bro, it's good.
So it's going this way, so it's going to keep going that way, but there's a force coming out of the board. Is it going to stay in the plane of the board? No, it's going to come out, right? So it's going to come like, it's going to kind of curl out.
Three-dimensional. Three-dimensional.
How do I draw that?
You don't. Just
Oh.
picture it inside your little head.
That's a bit much.
Okay.
I'm gonna draw it.
You try to think about it, your head just explodes.
Oh, your head's
So-
cute.
Just picture it like that. Okay, good. Now, we've learned before that the force is opposite on an electron, right?
You don't
Same thing
see
happens
these
here.
real life
We're
situations.
still using our right hand rules, but whenever we find the direction, we just flip it opposite for a negative charge. For example,
Right.
let's mix it up.
Yeah.
Let's say our B field points this direction. I think my blue marker is dying. Oh, yes.
No allergies. Only knees.
Oh.
So close.
Can I try?
Extra credit points
Go
for
try.
everybody.
Go try
I know how
it.
that feels, man.
I didn't do that.
I know you feel it. That shit be going all around the rim, bro.
I did not bet.
Yeah.
Wow.
That's all you can
I
do.
So,
hate nuts.
here's our B field
I like it.
with the green. Good enough. Okay. And let's say that we have
Jordan, how do you
Um,
make that? Send me the recipe.
an electron,
It's just,
and it's going
it has
down
to be
through the field.
That's what I think.
I taste that.
Okay?
It's doing something else.
Where's the force point?
Maybe, if I remember, I think
On the
it was,
electron.
macadamia nut.
The force is pointing
So,
down.
point with V,
Down.
bend with B,
Bend with a B.
It's
and our
going.
thumb points in the force for a positive charge, then flip it around.
Inside?
So,
Into?
pointing down,
Oh shit.
bend with B. My thumb points into the board for a positive charge, but since it's an electron, the force points out.
Can we have a hand lesson, like a mini
Oh,
one?
for real, I need a hand lesson. You
Because,
just
like,
lost me. I thought I had
Wait,
it.
you
I don't have it.
point, you point with V, you bend with B,
So-
Wait,
and then
wait.
First, you point with V.
Point with
So
B.
we're pointing down.
Okay.
Okay? So you should be able to twist your arm any way that you want
Right.
so that we bend where B points. B points that way.
Okay.
So I need to turn my palm so that it points that way, so that I bend my fingers.
Side jump.
Yeah, and then my thumb points where the force is.
We got it.
So into the board.
We're in there.
It's outside the board. 'Cause
Yeah.
Huh?
Nothing.
Okay. Good. All right.
Then it's off.
Very good. Very good.
Just let you do it.
So that leads us into our next challenge question. This is going to take some thinking.
Alright, so it goes with that. So it's like this. So it's like
Pay
this.
close attention to the things that we've talked about today.
It's going down and right. So it's moving to the right. And the force is going to the right. And then it goes down.
I don't know why you ask me these questions. I really don't. Okay.
I think it's going.
Is
out.
it into?
I think it's into the page.
Yeah, this one.
Oh, look at me, I'm learning. Mr. Maynard, good
I
job.
did it with my hands. You did.
Into? Wait.
I did it with my
You said
hands.
into the page.
Into?
It's
I did it with my hands. I was like,
You're saying like curl it right.
watch him be like, "Ha, you're wrong. It's out of the page." You forgot to flip your hand.
What's X? Okay. I don't think it's out. Alright, looks like we have lots of D's. There is a change to C.
Yo, better than Jordan. Come help me put this up here. Ow. I mean, help me. Come on.
She said she's gonna kill me. You just hear that?
Colleagues does it. 5, 4,
Didn't hurt nothing.
3,
Didn't hurt nothing.
2, 1. Done. All right. So mostly D's here. Oh, actually, yeah. Mostly D's. Let's see who's right. So first, where is the current pointing?
Down. Right?
Are you sure?
Yes. I don't like
The
this.
current points up because we always assume what?
You know what?
I'm
jumping.
Current. If the electrons are flowing down, the protons have to be flowing up if they are allowed to flow.
Okay, maybe I'm still not. Never mind. I give up.
Do you want to change your answers? Do it now. Second chance.
Wait a minute.
If you want to change your answers,
Wait, am I still? I'm so scared now. I don't like this.
You look too smug.
Oh my gosh, you look just like CSM. He gave us a pop quiz today,
should have
and
changed
he
it.
was just smiling.
We would have got all 6 points.
Out. It probably. Wait, it doesn't have to be 3D though?
Got all 6 points.
Doesn't have to be 3D.
Bro,
We should really get all 6
bro,
points.
now I'm lost.
well, if you didn't change your answer,
Oh, we changed our answer.
Wait, what'd you change it to? I thought it was the same. I still think it's the same thing. I have hope. I'm gonna believe in myself. I'm not gonna let you trick me. No, don't look at me.
I thought it was X at first.
I will not stand for the peer pressure.
You'll see, because we're going to get it right.
I thought it was B.
You'll see.
alright, so you all think it's C now, huh? I'm gonna call it done. 3, 2, 1.
Wait,
I swear.
you have 2.1 points.
Wait,
We have
what
problems.
page?
Okay, let's take a look.
That's not points anymore. It was
So,
it was like 1.
We've already established
Now it's
the
just
current
good.
points up. Okay, so before I can tell where the force is pointing on the proton here, I have to find out where the field is pointing. So I have to use my first right-hand rule, which is the curly one. Okay, so thumb points with the current. My fingers curl in a direction, going around in a circle around the wire. So since we are on the right position here, okay, so thumb points up to the right, the field points into the page. Okay, into the page. So
I don't like this game.
field points into the page to the right of the wire. All right. Now the proton is here, and it's a positive charge, and it's going V. So now we have to find out where our force points. So we point with V, bend with B. B points into our board. Our our force points up.
You know what?
No one got that right.
B.
I've accepted the fact
B
that I'm failing
is
this
correct.
game, so I don't even know why.
Wait. Oh no, you put it after L.
Why you rat me
I
out?
thought you actually got it right. No, I thought you actually got it right. I looked at him like, oh, somebody actually.
No, I
put B.
said it
See.
before the done.
You guys were all like, oh, let's jump on that C bandwagon. That's not why I chose that. Ah.
Why the hell are there pages
But
in physics
we
anyway?
learned from our mistakes.
Use influence everyone talking.
That wasn't even tickle. Just fucking.
Alright guys, we are almost done.
Yeah, it's shit funny, nigga.
Do you want a fiver or should we just
Fiber.
No, let's
Continue.
look it up.
How much do we have to finish?
Thug it out, thug it out. Thug it out, thug it out, thug it out.
Look it up.
Let's
Okay.
do it.
Alright, let's do it.
Thug it out, thug it out.
So
I'll be thugging my shit out.
let's expand this. Okay.
You are.
So let's say that we've got
You couldn't be
a
a young
magnetic
nigga
field
time.
in a region of space. Where does this field point?
To the
Jordan, smart.
Right.
Out of the board. Because there's
yeah,
the
the
points,
dots.
not the
The
x's.
dots, the dots.
Okay.
You're right.
So the field points to the right.
This class got me
I'm sorry.
sweating. I ain't even doing nothing.
Field points out. And let's say we've got a proton. Okay. And it's going that direction.
Okay.
Where's the force acting on this proton?
That direction.
See, now you have me second guessing
I
myself.
know.
I don't like this.
V.
Down.
Where's my B pointing?
It's
V points out of the
So
stage.
it's like down.
So V, B, force points down.
that's so dumb. Like this whole hand thing is so stupid. Like,
But it works. It works.
when I get it,
I thought we were using formulas. I'm using my hand and I'm still
How do
failing.
you determine what turns your hand?
So your palm is gonna be facing wherever your fingers will bend.
Well, yeah, but like what?
It's
why are you
I
curling your hand
You
that
have to
palm.
turn it so that you're
Yeah.
going to be bending towards B.
You see how B goes out and out of the page, so it'll
B
be
is
out.
pointing out. So whenever I
How are y'all seeing this
so
reading B
if
that
I
is pointing
have
out?
it here,
It's
that's
just
not out. That's not out.
He did like an arrow.
That's not
Just
out.
But
It's good.
so what if it's
That
going
is-
in?
Honestly, I've only
But
like,
last time it was pointing in.
Oh.
Last time it was.
How do you know it's pointing out or in? Does it tell you?
Because the problem will tell you.
It's like the weirdest
Yeah.
physics
Okay, we're
sign
good.
language.
I didn't know if there was like some sort of like thing I had to decipher.
No, no.
Okay,
Well,
cool.
Audible with test.
yeah, so-
Stop.
Your problem will tell you.
Okay.
There's a good chance that they will give you both in words and a picture.
Oh.
What's this supposed to say?
Makes
Just
sense
to
now.
make sure that you're abundantly clear where our B field points.
So if it
He makes sense now. That's
by
not
picture, what do you mean?
Like dots or X's.
So
everything is a shoe.
I'm stupid. I'm now. I got it now.
Okay. Because like there's gonna be another challenge question. Like, see those X's?
Yeah.
Yeah. So that means into the page.
Yeah.
But
So we're gonna
I
turn
named
it.
I
my
got
fish
you.
a he because it was.
oh
you.
my god, that makes sense.
That makes a lot of. I thought we were just
In
doing
and
like.
out.
Curtis just got it.
Oh, that makes so much more sense.
Thank you.
Light bulb. All right, good. So we know how to find our force down. We've had lots of practice. Now let's analyze what's happening with our motion, though. Okay. So it's going this way, but there's a force acting on it. What's going to happen with our track?
I'm gonna go parabolically down.
It's going to curl down, right?
Yeah.
But remember, our force, specifically the direction of our force, is going to change based on the direction of the velocity.
I see.
Because it's not like the electric field where the force is constant in one direction. Here, the force is going to change. So, as we curl here, okay, it's going to end up where my proton is now pointing down. Where's the force pointing now?
Still down.
No.
No.
It's pointing.
That
It's
way.
your right hand
Oh,
roll.
Up,
because-
right.
Don't gaslight
To
me.
the
Wait,
left.
it's going this way.
Wait,
This
I was
way.
just playing.
Outside the page. Wait. It's going down.
Is it going out?
To the
What?
left, right?
It's this
No,
way,
it's
right?
not out.
To the left.
To the left.
To the
Oh wait.
To the
it's
what?
that
To the
way.
left.
To the left.
Left.
V.
Everybody
Going down.
to the left.
Outside the
V.
page.
force.
I'm learning.
'Cause
Y'all suck.
This
I
means
used the
out.
wrong hand.
Yeah, right hand rule. Now, I know it is confusing because the book actually talks about a left hand rule. Okay.
That's what.
And if you look online, there's like a bunch of people who use the right hand rule and a bunch of people who use the left hand rule. Okay. Both of them work, just not at the same time.
It's from CSM's classroom, so it's tax.
But my suggestion is that you pick
So
one.
you have this
So
big ass bottle.
I'm
and
more
not a drop of
natural.
water.
It's more natural for me to go with the right hand, so I'm going to use the right hand rule each time. And you can do that for all of physics. Okay? Or you could do the left hand rule. If that's your jam, use the left hand rule for all of physics. But you don't have to change. You just have to pick one and stick with it. Okay? So, here we go. Alright, so this force points to our left. Alright, well, where is it going to make the proton go though?
To the left, like start spinning.
It's going to curl this way.
Yeah.
Yeah.
It's a circle.
Does it do a circle?
It's a circle.
Uh-huh.
Da-na-na-na.
It sure does. So now,
Yeah.
if our velocity points that
What's
way,
your waist is snatched?
where's our force pointing?
So you're
Up.
That way.
Points up.
Into the.
And that's going to make the proton take another right turn. And now the velocity vector points up. Where does our force
To the
point?
To the right.
To the right. It is going in a circle, is it not?
Yes.
Is it also
What do we need? What is responsible for motion in a circle?
I don't know. Is it an atom?
Centripetal force, baby.
No.
Yeah.
No. Get away.
Put it away.
Everything's coming back. We got motion, we got forces, we got energy, we've got circular motion.
Central.
Yes.
Wow.
It's all coming back full
It came
circle.
full circle. I like it. I like it.
Oh my
Stole my
God.
joke 30 seconds before I got to say it.
Remember, is the centripetal
Would've been
force
better if
a
you
new
said it.
force? No. So what serves the role here?
Gravity.
Nope.
That's funny.
Magnet.
Circle.
Velocity's not a force.
Magnetics.
The magnetic force.
I was just
I know she's
playing.
guessing. I know
Yeah,
my
because this is the
dumbass.
force from the magnetic
I
field.
said it first.
That's the only force that we're talking about here. So,
Oh, I ate.
again, once we identify what force serves the role as centripetal force, we set them equal to each other. Fc is
I've been
equal
on a
to
roll
Fb.
today.
Now Fb, we know that our velocity is exactly perpendicular to the B field, so the sine of 90 is 1, so it's just QVB, okay? So QVB, right there. Remember our centripetal force equation?
I got 3 right now.
mv squared over r? That's okay, I got you.
Sure. Thank you.
Alright, and then we're gonna solve for r, because I want to know, what about the radius of the circle? How big is the circle? What determines how big the circular path is? So we're going to solve for r, move that over, and we're going to divide those guys. So mv squared divided by qvb. That v cancels out with one of those, and I'm left with my m times v, which happens to be momentum, remember?
Oh, yes.
Yeah,
I do remember.
divided by q and b. Now, this equation is not in your equation sheets. You may have to derive it like we just did. Like we did for all of the other circular motion problems.
No.
Yes.
No.
But notice, so these four things will determine the size of the path as we track this, okay? In your books on page 475, these four graphs are a pictorial representation of this equation. What happens as we increase or decrease mass, or the speed, or the charge, or the B field, how do those affect the size of the path that it goes in a circle? So real quickly, okay, if we've got a larger mass, larger radius, so it doesn't curve as much, It's a nice and big curve. The faster it's going, the larger the path is. However, these two guys are inversely related. So the larger the charge is, if we have an alpha particle, which is a +2, as opposed to a proton, which is a +1, the more charge we have, the tighter the circle is. And the stronger our field, the tighter our circle is as well. Okay. All right. Now, let's take a look and see this next question.
Particle, the charge Q is
I think all science teachers sound the same.
Right?
Yes.
No.
Because we're just so excited about science.
Exactly, and y'all like to slide around the classroom. So fun.
Who else slides around?
Miss Daly, my biology teacher, and it was his first year teaching.
Miss Daly does not slide around.
Miss Daly slid in those slides. She slid.
Oh well, she did slide around actually, but
She did.
She sat down mostly.
No, Miss Daly was sliding, or she was in her chair judging me. Either way.
I don't think
Chair
it was
judgment. Is that what you
judge
said?
you.
I like it. I should get a chair judgment.
No.
Like a big throne.
Oh no, but she just sit there with her legs
And then I
crossed.
can do
Dana?
the whole like thumbs up or thumbs down.
Oh no, she'd just be like, Dana, come here.
Kind of like that.
So, why did you do this ma'am? I don't want to talk about it.
I remember whenever she used to come over and talk to me, and she just
Alright, we should have some
Increase
cigarettes and coffee.
Alright, looks like we got
Cigarette
A's are the
versus
popular
not
ones
ever
here.
gonna
Are you
put
sure?
A.
Set it first.
What do you think it's A?
Alright, I'm gonna call it down 3,
Oh, yes, you put A.
2, uno.
I'm sorry.
Done. Okay, here we go. So, a particle with charge q is accelerating from rest through a potential difference v over a distance s. Remember, we talked about how the kinetic energy of a charge was based on the charge times the times the voltage or the potential difference that it accelerated through. Okay, so it's sped up initially, and now it's going through a magnetic field at right angles, so it's just QVB here. What single change will make the radius of the curvature of the path of the particle smaller? So we're looking at this equation, which again is not on your equation sheets, but we're trying to find out what is going to make this smaller. So a smaller mass will do it, a smaller speed will do it, a larger charge, and a larger field. You guys all said A. I don't know why this said P instead of just staying with B, but that's okay. We will make it work. So if we increase P, if we increase the field, that will decrease the size of our R, and A is correct. Yes. B is a little tricky. See, at first when I read this problem, I was like, okay, well, but what if we decrease the distance that it accelerates over? Like, in my mind, I'm like, okay, well, if it accelerates over less distance, then it's going not as fast. So the v had to be decreased. But then I caught myself, and I'm like, okay, well, the distance, remember, the d actually canceled out when we came up with this equation. Okay? The distance doesn't actually matter. It's all about the potential difference. So if we've got a 1v this way or a 1v this way, it's still 1v. So the distance doesn't actually matter, but the voltage does. So A was the correct answer. Good job, guys. 1, 2 your points. So A here, we've got Elijah. Yeah, so Spice Girls taking first place, followed by Quantum taking second with that quick change. And then we got Up and Adams in there with that third position here. Okay, all right, we got one more. One more. Are we ready for this?
We're done.
Yes, we are.
Done.
Oh, hold on. I gotta zoom out.
I need to leave. I can't leave. You You look so much like John.
That's
John tastes so bad.
all right. Last challenge question, and then I have something to show you in the back.
That would just be disrespectful.
What? Starts whining.
What you say?
Huh?
I'll wait till after school at 6 o'clock. You want to practice? Of course not. My gosh.
Hey, Dana. Dana. Let's focus on the problem.
I'm not going to get it right.
Well, at least you can try.
She got 3 right so far in her whole career, and it's all been today.
What was the weekly moral a couple of weeks ago? If I
You miss 100% of shots you don't take.
if I don't try something, if I do something
Where's purple?
to stop me, I don't know.
See, I didn't even pay attention. I didn't even know there was one until you just said.
I'm not gonna change my vision.
It's gotta be larger.
I did it all by myself.
It's larger, right, guys? It's oh, so it's no A or B.
It's like these are the popular answers.
I think it's
here.
B.
Like, let's go. I'm actually a genius, bro. Like, I might be that guy.
I gotta call it done now. 3,
Hey, Dante.
2,
It's going
1,
down. So it's already negative.
done.
Please tell me I'm right. If I'm not, I'm going to be really sad.
Well, let's see.
I'm gonna be
Alright,
really
so
sad.
you have the 3 particles with identical charges, so same charge, okay? But different masses is shown as they enter a region of uniform field. The particles have the same initial velocity. So the charge and the velocity and the field strengths are all the same. So there's only a difference of the masses here. And notice that the mass is directly proportional to our R, okay? So if we're looking at particle X compared to the other 2, which aren't named, that's okay. They don't need to be named, okay? But X looks like it has a wider circular path, and the others ones have a smaller circular path. So if R is bigger, that means that X has to be more massive. Okay, so more mass, which means A or B. So far we're good. All right, so then the next thing is, what's the sign of the charge? Okay, now we do know that the field is directed into the plane of the paper, so it tells you in words and it gives you a good picture. Okay, so, and we know that they're all going in this direction initially. So we just gotta have our right hand rules going. So point with V, bend with B.
Correct.
And then the force on a positive charge would point up.
Let's go.
So this guy was positive.
He's putting down.
But the question is asking for the X, which is going to slow down, which means that it's negative. B is the correct answer. Yes.
I'm a goat.
Fire.
I'm a legend. I'm a day one. I'm an ancient Mesopotamian.
Not too
I'm
much.
a guy only found in Greece
Seriously.
and Rome.
What's your YouTube channel?
Tara in second.
I not share you?
No.
And Up and Adams.
My YouTube channel is better than yours.
Write it
All right,
down.
last thing, to join me at the
I'll
back
show you
table.
after.
All right, so if you read the book, it talked about an electron gun or a cathode ray tube. This is exactly what it is, okay? So that beam is a beam of electrons, and it is filled with a particular gas that makes it glow a particular green so that you can see it, okay? So we also have, so there are big coils of wire that are around this particular globe, okay? Now, there are a couple of different things. One, I could change the electric field. Right now it's not on, but here, so if I click the, oh, sorry, that's going to be the power of the guy here, yeah. So if I click the electric field on, I'm increasing the electric field as it flows. Well, which way is it flowing if these are electrons?
Down. Right.
So So the force acts opposite the direction of the field on an electron. So since we know that they are being deflected up by that constant electric field force, okay, then the field has to point down. And the stronger it is, the stronger the force is, and the more of the deflection we have, okay? But see how it only is curved within the little pieces of metal. That's where the E field comes from, because they put charges on those two pieces of metal, just like we did up there. But then once it exits the region, it continues in a straight line, or straight line. Yeah. All right, good. And then, of course, I can change the direction of the E field and make him go down. All right. But now let's take a look at the magnetic field, which we talked a lot about in class. All right, so right now I'm going to flip this. So this light means that the coils are going to have a current that's going to flow in this direction. So that's going to be a clockwise direction. Which direction will the field point due to that current? Well, there's only two ways to go. This way or this way. Since it's going clockwise here, it points in. Okay? And if it points in, so if our field points in, the V points right, which direction will our force point on these electrons? So V, B, force points down on a positive charge, but it points up on an electron. So as I add in the current, you'll see it curve up.
Oh, wow.
Now, I'm increasing my B field. So as I increase my B field, remember the B was on the bottom of the fraction. So as I increase my B field, the R shrinks. And the circle gets smaller and smaller. Now, I could also turn this tube. If you're close enough, you see that it doesn't actually make a full circle because it's actually not pointing in this direction. It's actually pointing, or not pointing in this direction, it's pointing in this direction. So you'll see a helix shape or a spiral pattern if it were to continue moving through space. It's not just a circle in a plane, it's going to keep going in 3D. That's cool. All right, let's put that back. Okay, so I'm going to reduce the field strength here, go back to the same. Now I'm going to flip it around. Now my light shows, oh, now I'm going in a counterclockwise current fashion. Which way is our field pointing now? Out of the board here. Okay, and then so where is my force pointing now?
Up. Wait, down.
Up for a proton. So these are electrons.
Down.
So this should be down. So it should curve down as I add the current, as I increase my B field. Oh, look at that. It doesn't actually have enough room to make a full circle because it runs into stuff. But there we go. Cool stuff. All right. Good job, guys. We are done.
Yay! How expensive is that?
I think it's like $600.
Gosh.